So we have learned about F vectors and matchings. So now what we want to do is we want to count matchings in a graph. There are several tools that we have learned in undergraduate graph theory which tells you whether a given graph contains a perfect matching or not. But once it has a perfect matching, we are also curious how many perfect matchings are there in the graph. So what we want to do is we want to count perfect matchings in graph. And one of the tools that we can use to count matching is the concept of permanent in matrix. So say permanent and matchings. So one of the ways to deal with graph G sometimes is consider a matrix which contains the information about graph G. Sometimes the entire graph can be viewed as a matrix in some way. So one of the way is consider adjacency matrix, which we learned in undergraduate graph theory. So let's start with some simple situation of balanced bipartite graph. Let's say we have a balanced bipartite graph. We are considering balanced graph because if bipartite graph is not balanced, we anyway don't have any perfect matchings. And this balanced bipartite graph has partition U, W. Say these vertices has labels. U consists of the vertices from U1 to UN, and W consists of the vertices from W1 to Wn. And for this graph, we consider a bi-adjacency matrix. Which consists of the coordinates, the components of the matrix, where its Aij is 1, if Uiwj is an edge in graph G, and it is 0 otherwise. So for example, if we have graph, say U1, U2, U3, W1, W2, W3, and let's say this is the graph, then its bi-adjacency matrix is that you take a matrix and you name each row corresponding to its vertices in U, and each column gets a name which comes from the vertices in W. And then the component is either 0 or 1 depending on the adjacency. If you have a graph G, bipartite graph G, then we can consider this matrix. And conversely, if we are given this matrix, then we can construct a bipartite graph G. So this matrix contains full information about your graph G. In here, we can consider some parameter which is called permanent of this matrix A. For a given matrix A, let's say square matrix, the permanent let's write per A of A is defined as following. So we take all the permutation and we take these entries of the matrix depending on this permutation, and where the summation runs over all permutations on Brachiden. So for this particular matrix A, we know that permanent of A is, there are 6 permutations, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. But out of those 6 permutations, it's easy to check that only the identity permutation is a multiplication of 3 ones, and everything else has one component which is 0. So you can actually check this is permanent is 1. And in this G, graph G, if you want to count the number of perfect matching, you can see that this is the unique perfect matching. So let's write PMG to be the number of perfect matching in G. Then we know this is 1. So let's define PMG be the number of perfect matchings in G. And it's easy to actually see that for this biadditions matrix A, and G is a balanced bipartite graph, then permanent of A is same as the number of perfect matching in G. Because if we have certain perfect matching here, then that that pairs UI with certain WJ. Let that J be, say, sigma of I for some sigma. So for each perfect matching, it has, this correspondence. And this sigma has to be a bijection between Brachiden and Brachiden. So it is a permutation of Brachiden. So once we have a perfect matching here, that corresponds to a specific permutation pi. So here this sigma could be one of this pi. And then there, this term becomes 1. Because these two are matched, means that AI sigma, pi I is 1. So this term becomes 1. On the other hand, all the other terms here, which does not correspond to perfect matching in the graph G, there, this term, this specific pi does not correspond to a perfect matching in G, means that sum of I pi I here, I pi I is not an H in G, which means this is 0. So if some permutation pi does not correspond to a perfect matching in G, that means this term vanishes. So all the terms here becomes 0 if it's not corresponded to a perfect matching in G. And for those that corresponds to a perfect matching in G becomes 1. So this permanent of A actually exactly counts the number of perfect matching in G. So let's say this is observation. We know this. So now, we want to count the number of perfect matchings of a given balanced bipartite graph G. Now all we have to do is to compute its permanent. But one problem is for given matrix, in general, it is difficult to compute its permanent. If you see, this permanent has this formula which looks quite similar to the formula for the determinant, except in the determinant you have to multiply -1 to the, say, sine of pi in each term. But in permanent, we don't have this. That, you can say that difference is small if you want to say it's small, but it actually causes, considerable difference in computing. Because in computing determinant, we can use the row operations, and we exactly know how it changes the determinant. So we can use the Gaussian elimination method to effectively compute the determinant of a matrix. So you can compute a determinant of a matrix in polynomial time, but permanent are not so nice. So it's, in general, difficult to compute. Anyway, still we can use this permanent to get some inequality, some bounds on the number of matchings in given bipartite graphs. So one of the theorem regarding this providing bounds on the number of matching is this. Let's say before actually writing the theorem, let's define something. And we call a matrix doubly stochastic if it is non-negative, meaning that every entry of the matrix is non-negative, and all its row sum and column sums are 1. And it's known that if we have a doubly stochastic n by n matrix, then we have a lower bound on its permanent, which is n factorial over n to the n. Say n with equality if and only if every entry of A is 1 over n. So using this theorem, we can actually found the number of, found the lower bound for the number of perfect matchings in K-regular bipartite graph. More generally, K-regular bipartite multigraph. Because if we have a K-regular bipartite graph, then it's immediate that this G is actually balanced bipartite graph. because of the regularity of the degree. So you consider its biadjacent matrix A, and then you consider 1 over k times A. Because this is k regular, every row sum and column sum are k. And by multiplying this 1 over k, this becomes doubly stochastic matrix. So permanent of k A is actually at least n factorial over n to the n by this theorem. And from that, I mean, we know how permanent changes once we multiply by scalar. So we can conclude that the number of perfect matchings in G, which is same as the permanent of A, is n factorial times k over n to the n. So this provides a lower bound, and we will not prove this theorem. Its proof is not so combinatorial in some sense. So we will not prove this theorem in this course. And similarly, so this provides a sharp lower bound on the number of perfect matchings in k-regular bipartite graph G. For the same setting, we want to also find the upper bound on the number of perfect matchings of k-regular bipartite graph G. And for this, the following theorem actually provides a upper bound. So this is something called Brexman's theorem. Let A be a, say, 0, 1 matrix with row sums R1 to Rn. Then what we know is the permanent of A is n most R1 factorial to the 1 over R1 times R2 factorial to the 1 over R2 times ... to Rn factorial to 1 over Rn. So this provides an upper bound. So if we only consider the k-regular bipartite graph, then its biadjacent matrix satisfy these conditions with R1 and Rn all being k factorial. All being k, sorry. Then what does this provide? It says that you take k factorial and then n over k. So this provides an upper bound on the number of perfect matchings in k-regular bipartite graph G. And also this is sharp. This is best possible because you can consider graph G to be the collection of complete bipartite graph with k vertices on one side and the other side, and you take the disjoint union of this, many of them. Then here you can easily see that there are k factorial bipartite k factorial perfect matchings here. Then the total number of copies of complete bipartite graph is roughly n over k, depending on the parity of n. Let's just assume that n is divisible by k. Then if you want to count the perfect matching, you just count the perfect matching in each component and you multiply together. So this is exactly the number of perfect matchings in here. So now we want to count the, we want to prove this Bragman's theorem. So how we will do is we want to design some random algorithm and then define some random variable which estimates the permanent of A. But it not only estimates this, but it's overestimate somehow. So let S be the set of permutation sigma, which is permutation between a permutation of bracket n, which satisfy AI sigma I is 1 for all I in n. So this is you can consider it as a perfect matching chosen as random. No, sorry. Forget what I just said. So you can consider this S as a collection of all perfect matchings. And what we will do is we will do some random procedure. So we pick this one random permutation sigma in S and tau in Sn. So tau is random permutation and sigma is a random matching if you want to consider it that way. And both are chosen uniformly, independently, and random. And we let A1 be the original matrix. And we delete row tau 1 to tau I minus 1 and column sigma tau 1 to sigma tau I minus 1 from this A1 to obtain AI. So what we will do is, let's say we have 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, some matrix. Then vaguely what we are doing is you choose a row tau 1, and then in this row you choose one entry which actually extends to a perfect matching, extends to a permutation in S. And then you delete this and this. Then remaining matrix is A2. And then you repeat. You take tau 2 or random row, and then according to that row, you choose a one column, and then you delete that. Then remaining one is A3. Then you repeat. So you can consider this as choosing one by one, tau 1 first, and then sigma 1, tau 2, sigma 2. You can consider it that way, or you can consider it that tau and sigma are pre-selected at the beginning with a certain probability distribution. Anyway, while you're doing that, what we want to do is the following. We let R tau I be the number of ones of row tau I in this matrix AI. Then this is always non-zero, as the sigma is chosen in such a way that this value is always 1. So sigma was chosen from S, and S is the set of permutation which satisfy, this equality for all I. So what Ri is that once we chose tau 1 and sigma tau 1, so we delete this and this. But before deleting it, you count the number of ones, so which is 2. No, so R2 is 2. And then you choose R tau 2. Now in this row, there are 2 ones surviving. So tau 4, this is 4, this is 2, is again 2. So this is all again a random variable. You randomly choose one row, and then you count the 1, and you write it, and then you delete it, and you also delete one of the columns which contains 1 in this cross. And then you again choose one row, and then you write down the number of ones in that row. And then there you choose one column and then delete. You repeat this. And we define random variable L, which depends on this sigma and tau. As sigma and tau are fixed, then these numbers Ri are all fixed. Once sigma and tau are given, then you can compute this. This is deterministic. But this is random variable once sigma and tau are chosen uniformly and random among S and Sn. And you just consider the multiplication of all of this. And what we will claim is that this L provides a estimation of the permanent A. So why is it? Intuition-wise, let's just say you have this 1, 1, 1, 0, and then let's say tau 1 is the first row. And let's say T1 is the permanent of A1, say T2 is permanent of A2, T3 is permanent of A3, where A1 is the matrix you obtain from deleting first row and first column. A2 is you deleting the first row and second column. A3, you delete the first row and third column. So this matrix is A1, and this matrix remaining thing here is A2, and so on. Then it's obvious that the permanent of A is actually T1 plus T2 plus T3. So we don't consider T4 because this is 0, so all the terms containing this vanishes. And sigma tau 1 could be either 1 or 2 or 3. It's never 4 because of this condition. And we choose this sigma out of all S. And S can be partitioned into 3. S1 and S2, S3, where sigma tau 1 is 1, and sigma tau 2 is 2, sigma tau 3, sigma tau 1 is 2, sigma tau 1 is 3. Depending on its value, you can partition S into 3 sets, and this has size T1, and this has size T2, this has size T3. Because this permanent counts the perfect matching, and then this S is a collection of perfect matchings. It's formally a set of permutations which satisfy this condition. which is exactly the, same as this permanent calculation. As we are choosing one of them at random, so let's just assume T1, T2, T3 are in this order. T3 is the biggest. So probability that as this sigma is randomly chosen out of this S, the probability that this is deleted is T1 over T1 plus T2 plus T3. So if we assume T3 is at least as big as T2 and T2 is at least as big as T1, then it's more likely to delete the third one in this process. And it's more likely to delete the second one than first one, and it's very less likely to delete the first one. But when we deleted it, the remaining thing, we have to measure it again. So what we do is, instead of computing this, what we do is we certainly just write 3. In this case, the R1 is 3. So we write down 3, and then we keep estimating the remaining permanent. And it's more likely that so remaining permanent could be one of these 3, but it's more likely that the third possibility is more probable than the other 2. And then second one is more probable than first one. So remaining computation tends to give a permanent of a matrix. Give some number which is estimation of the remaining, estimation of the permanent of the remaining matrix. So this tends to be more closer to, say, T3 than T1. Then 3 times this number, permanent of remaining, say A2. And it's more probable that this is closer to T3 than T1. Then 3 times that number should be bigger than the permanent of A. So I hope this can provide you some intuition why this procedure would give you an overestimation. You choose one row and you choose one column and delete. You keep doing that. While you're doing that, before deleting the row, you count the number of ones in there, and then you record it. And then after all, you multiply all the recording. Then it must provide you some, overestimation of the permanent. So, let's make it more rigorous in the next video.